I don't know. Let's see. Okay.
All right, we can see your slides.
Okay, great. Yes, so as Kirsten said earlier, distribution network is becoming more and more important, yet the measurements are not as complete as in, say, transmission networks. And therefore, that's the motivation for these talks. As we know that distribution network will have more and more distributed energy resources like solar panels, storage, EV, smart buildings, smart appliances, demand management, and so on. And therefore, this is both a risk and opportunity. It's a risk because you can introduce additional uncertainties, random fluctuations, frequent fluctuations in, say, supply, in demand, in power qualities. But yet it's also an opportunity because these are active distributed energy resources that sometimes may be capable of real-time communication, computing, and actuation. And therefore, it enables dynamic feedback, which could improve robustness, security, and efficiency. So that's the motivation. So it consists of 3 pieces of work. I want to acknowledge my coworkers. The first piece is about learning the topology and impedances of distribution grid, or learning the admittance matrix Y. And it's joint work with Yue Yan, who is now at Huazhong University of Science and Technology, Omid Adokanian at University of Alberta, and also Claire Tomlin at Berkeley. And the second piece is adaptive charging network and also a research portal, a research facility for electric vehicles. It's work of my former PhD student, Zach Lee, who's now with a PowerFlex, a Caltech startup. Sunesh Sharma, who used to be at Caltech, is now pursuing PhD at Berkeley, and Thompson Lee, who's a graduate student at Caltech, and also many others. And the third piece is really the work of Guanan Xu, who about learning-based voltage control on distribution grid. He was a postdoc at Caltech and is now a faculty at CMU EECOM. So the first and the third piece are theory, and the second piece is implementation and deployment. So common to all of them is some learning and some control on distribution grid. Okay, so let's go to the first piece about learning admittance matrix Y. So I will first formulate the problem, and then I would focus on a surprising result, surprising for us, that for a radio network, even though you may not have measurements of voltages and currents everywhere, you will be able to recover exactly the original or the ground truth Y matrix. So there's no noise. So we'll see the details of that. Okay, so the model is very simple. We have a network which is represented by a graph. N bar is a set of nodes or buses, and E is a set of links or lines. So here's a picture on the left, bottom left, that you have a graph, some buses or nodes connected by some lines. And each line, JK, is parameterized by its series emitter YJK. So here we assume the charging admittances YJKM and YKJM in both directions are 0. So this is a reasonable assumption for distribution systems. For a standard pi model of the bottom right, then here we assume the YJKM and YKJM, the shunt admittances are 0, and the line is parameterized by just the series admittance YJK. Okay, so that's the simple model. And admittance matrix is really expresses the current balance at every node and also Ohm's law. So the first equation Ij is the current injection from node J to the rest of the network. And it is equal to the sending end current from J to K over all its neighbors K. And you can express IJK, which is the sending end line current on JK, in terms of the voltages at Vj and also at its neighbors Vk. And the first equation is the current balance plus Ohm's law at every node J. If you write it in vector form, then you get this I equals Y of V where I is the vector of current injections at every node in the network. V is the voltage phasor at every node in the network. So both I and V are complex, n+1 complex vectors. Y is this n+1 by n+1 matrix whose JK entry consists of the series of admittances JK at off-diagonal entries minus YJK, and the diagonal entry is a sum of the YJKs. And therefore, the matrix Y is a complex symmetric, sometimes called Laplacian matrix, but important thing is it's complex symmetric, but not Hermitian. It's a complex symmetric matrix with zero row sum. And therefore, for us in this talk or in this model, any complex symmetric matrix with zero sum can be interpreted as an admittance matrix, which means that if you give me a matrix which is complex symmetric with zero row sum, then I can associate an underlying graph which can represent a power network with your matrix. Okay, so we'll use this later on. Okay, so and therefore the main equation for us is this I equals YV vector equation. And learning admittance matrix Y is the following problem. Suppose we measure the current injection phasor and the voltage phasor at every node I for capital T times. So we get these capital T measurements or pairs of measurements, VIT, VIT. We form them in a matrix, then you get I equals YV for every time T, going from 1 to capital T. So that's the IT YOVT. Or you can think of that if you line them up, each column represents each time, then you just get a matrix on the left, product of two matrices on the right. If you look, okay, great.
Oh, I apologize. Yeah, Professor Stephen Low, and do you mind to turn off your video? Because there may be some issue on our side, maybe also
sure.
at your part. Yeah.
Let me do that. Turn off my video. Okay,
right.
Great.
Okay. Yeah, much smoother. Thank you.
Okay, sure. Let me go in. Okay, great. So at node I, or if you look at the ith row, or it should be row, but you have to turn it around, then you can rearrange it to get on the left of the equation at the bottom, you get I, or the current at node I at each time 1, time 2, up to time capital T. So if you turn them around, you take the row and then rotate it, you get a capital T dimensional complex vector that represents the current phasor measurement at node I for all times. Similarly, on the right-hand side, you get the admittance matrix Y, the ith column of admittance matrix, YIF1 to up to N. And then if you rearrange your voltage measurements at all nodes, 1 to N, at all times, 1 to T, you get this T by N dimensional matrix V capital V superscript T. Right? So just a notation at the bottom right, there's a superscript T, but with two different fonts for T. VT represents a T by N matrix. So that superscript T is just an index. Whereas this the second font, V of T, represents the transpose. We'll see a bit of transpose, but most of them is the index. Okay, so basically this is the set of equations that we work with. And the question is that given these measurements of I, T, and VT, can we identify the matrix Y? Okay, so you can, that's the basic formulation, and there are many variants you can think of. For example, what happens if you have a noise, and what happens if you don't have measurements at all nodes, and so on. And then there are different ways, literature on variations of this problem. So here's one formulation where you look at you basically look at the errors, the difference between the left-hand side and right-hand side. Suppose there's a noise or the error term, then the difference between the left-hand side and right-hand side of the equation on the screen will represent the error. And therefore, one reasonable formulation is to say, I want to choose the Y matrix, it should be n plus 1 by n plus 1 matrix, so as to minimize the L2 norm of the error, subject to the constraint that Y is complex symmetric and it has 0 row sum. So those two constraints that basically represents the properties of any emittance matrix for us is complex symmetric, 0 row sum. Okay, and then you can formulate this, and you can have different ways to solve this. And if you assume different properties of the noise, you may be able to prove different, say, sample complexity results and so on. So for us, we're going to look at a simple version of the noise, but focus on the case when we don't have measurement at every node. So the simple version is that if this matrix V of T has full column rank, then this solution, you can identify an exact solution, a matrix Y opt. By exact, I mean that the error is 0. So informally, what it means is that in the noiseless case, if voltage measurements are sufficiently rich, then we can recover the ground truth Y. So that's roughly what that means or implication. Otherwise, your matrix will incur the least L2 error. Okay, so that's one formulation about learning emittance matrix A. But I want to focus on the following problem, which is that what if we don't have measurements at all nodes? Okay, so it is the setup is that, so we want to learn emittance matrix with hidden nodes. And the setup is that we have a radial network, which means it's a tree topology, is connected, so it is a tree, single tree. It's a single phase model, or you can think of it as a positive sequence model of your network. Approximately, that's you ignore, you assume the 0 sequence network and also this negative sequence networks are negligible. And you just look at the positive sequence network, then you get a single phase model. So that's the assumption. And we have measurements, let's say there are H hidden nodes, and therefore the measurements, let me label the first n minus H or n plus 1 minus H. I changed them. But the first set of nodes are what's called the measure nodes, which means that we do have measurements for both the voltage at the node and also the current at the node. And the remaining H nodes also in this H represent both the number of hidden nodes, but also denotes the set of hidden nodes. So the assumption is that we don't have measurements at the hidden node I, but there's also 0 injection. So this is reasonable whenever you have injection, either it's a generation or a load, typically you will have a meter. And therefore in the, say, network node inside the network, then there's no injection. There's no measurement, but there's no injection either. So it seems like a reasonable assumption. And then there's technical assumption that we'll need later on, that every hidden node has degree at least 3. Okay. So that's the basic setup. And again, because at each time t, we don't have measurements at the hidden nodes. So we can separate the set of nodes into group 1 and group 2. Now, I1 and I2 represent the set of nodes that are measure nodes in M, and the set of nodes that are hidden nodes. So everything, say V2, represents the voltages at the hidden nodes. So we can partition this I equals YV equation into this form, where the second set of the hidden nodes, at the hidden nodes, the current I2 is 0. So that's the main structure, that there's a 0 injection at the hidden nodes, and therefore you can do a current reduction, and the picture looks like this. So this is the measurement situation at each time t. We get I1 at the set of measure nodes, and then you get V1, V2, but we only measure V1, and we do not have V2 measurement. And we can do a Cron reduction and you get Y bar, which is basically the shear complement of Y22 given by that expression. And this Y bar characterizes the relationship between the current injection at the measure nodes and the voltage phasors at those measure nodes. So we get I1 for each time t, you get I1 of t equals Y bar of V1 of t. Now notice in this equation of I equals YV, only measure nodes are involved. And Y bar represents the relationship between voltages and currents. So pictorially on the right, that's what happened, that here you see a network with 7 nodes. Node 7 in the middle is a hidden node. The other 6 nodes are measure nodes. So at the 6 nodes, we have voltages and current measurements. At the 7th node, there's no measurement, but there's no injection. There's a voltage, but zero injection. When we do the Cron reduction, then what we see is a network with 6 nodes. Those are the measure nodes without the hidden node. And the connectivity among them will appear as the network at the bottom right. Right? So this is the Cron reduced graph. Okay, so suppose we can exactly recover Y bar, right? Because if you look at the Cron reduced network, we have measurements of voltages and currents, and therefore we can plug into the minimization problem where we learn Y, and under the assumption that the corresponding matrix of the voltage measurements has full column rank, then we can exactly recover the Y bar, which is the Cron reduced admittance matrix. So suppose we can exactly recover Y bar from the measurements, partial measurements. Can we identify the original admittance matrix Y from Y bar? Surprisingly, the answer is yes. Which means that we can exactly recover both the topology and the impedances of the original network. Right? And the proof is by construction. So I will try to outline the major intuitions or steps in the proof. Okay, so just recall the assumptions we have. So this collects all the assumptions we have underlying this. It is a radial network with tree topology. Is connected and assumes a single phase model as the model that we saw earlier. We assume the charging admittances are 0, and at every hidden node, the injection is 0, and every hidden node has degree greater or equal to 3. And also we assume that we can exactly recover the Cron reduced admittance matrix Y bar from the measurements at every node in M. Okay, so that's the key assumption. Most of them seem reasonable. I guess the one that perhaps is the least reasonable is a single phase model. So in distribution systems, it's typically many parts of the network, typically they are unbalanced and 3-phase. So we may not be able to represent it accurately by just a positive sequence network, for example. Other assumptions seems to be reasonable. Okay, so that's the assumption, and the result is that under these assumptions, we can recover the exact original admittance matrix Y. All right, so let me outline 3 key observations that give it an idea of how we might construct the original Y from Y bar. Okay, so now we have this Y bar, which is the admittance, Cron reduced admittance matrix, and we can decompose them into Y1 bar and Y2 bar. Now I will describe what's known and what we need to compute, right, to construct the original Y. But at least conceptually, we can write Y bar in terms of Y1 bar and Y2 bar, where Y1 bar and Y2 bar are defined in terms of the 3 submatrices of the original Y, right? So if you recall, original Y has a decomposition of this Y11, Y12, Y21, which is a transpose of Y12 and this Y22. So the original Y admittance matrix is characterized by 3 submatrices, Y11, Y12, and Y22, right, is symmetric. With this partition submatrices, then conceptually we can define Y1 bar as shown here, and also Y2 bar. And Y bar, which is the Cron reduced version of the admittance matrix, is the sum of the two, right? So conceptually, we can decompose Y bar, right? So we know Y bar, but we don't know Y1 bar and Y2 bar individually. So that's the first concept. The second concept is that, as I mentioned earlier, if you give me any complex symmetric matrix with zero sum, I can associate a graph, right? And therefore, conceptually, if you can show that Y1 bar and Y2 bar are indeed complex symmetric matrices with zero sum, and therefore I can think of them as an admittance matrix of some graph G1 bar and G2 bar, right? And also the Cron reduced admittance matrix Y bar has an associated graph, which is G bar, right? And therefore, the second concept is that there's a graph G1 bar, G2 bar, and G bar, okay? Now, just to reiterate, so what do we know? Well, we know Y bar, so that we can compute from the minimization, and therefore, we know G bar, right? If you give me a matrix, I can write down the corresponding graph, which gives me only the topology, but also I can label the nodes using the admittances. What we do not know are the components or submatrices of the original matrix Y. So these are the submatrices Y11, Y12, and Y22. And therefore, we do not know Y1 bar and Y2 bar. Okay? But it turns out that even though we don't know Y1 bar and Y2 bar, we can actually construct their graphs, G1 bar, G2 bar, from the graph G bar of the Cron reduced matrix. And moreover, as we'll see, that from this graph G1 bar, G2 bar, we can actually construct what is Y1 bar and Y2 bar. So this is the first key observation. So more specifically, what you can show is that the graph G bar underlying the Cron reduced matrix Y bar is this sum or direct sum of G1 bar and G2 bar. So what it means is that G1 bar and G2 bar are two graphs with the same set of nodes. Their edges may be different. So the edges are E1 bar and E2 bar, they may be different. And by that direct sum, it means the set of edges for G bar is simply the union of E1 bar and E2 bar. That's what it means. So you can show that even though I don't know Y1 bar and Y2 bar, and therefore presumably a priori, I do not know G1 bar, G2 bar, but I know that the direct sum is the graph G bar, which I do know, okay? Secondly, you can show that G1 bar and G2 bar have a very simple structure. G1 bar is a disjoint collection of trees. So basically G1 bar is the forest. G2 bar is a disjoint collection of maximal cliques with at least 3 nodes, okay? So, and moreover, you can construct G1 bar, G2 bar from the graph G bar very efficiently. So the right-hand side is an illustration. So the upper graph is the Cron reduced graph that we saw before. Given this Cron reduced graph G bar, we can construct G1 bar and G2 bar, which are shown, the two graphs shown at the bottom right? And therefore you see that G1 bar is a forest and G2 bar consists of these maximal cliques of at least 3 nodes, and also individual nodes without any neighbors. Okay? And moreover, this also shows that E1 bar and E2 bar, the set of edges in the two graphs G1 bar and G2 bar, are disjoint. And so that's important. So what is the implication of this? The implication is that we can actually construct Y1 bar and Y2 bar from the Cron reduced admittance matrix Y bar, right? So we know Y bar from the minimization, and by constructing G1 bar and G2 bar, we can actually now construct the Y1 bar and Y2 bar, these two Laplacian matrices, okay? So that's the first insight, that you can actually decompose the Cron reduced admittance matrix Y bar and its graph. The implication of this is that now I can identify nodes in the network into 4 types. So the measure nodes and hidden nodes. So now, because of the way that the previous observation, the decomposition, what it means is that for the set of measure nodes, I can actually identify which one are internal nodes that connects only to measure nodes, so they don't have any direct neighbor that are hidden nodes, and boundary measure nodes. So those measure nodes whose neighbors are both another measure node and also a hidden node. Now, in the set of hidden nodes, we can also have boundary. This is just definition: boundary hidden nodes and internal hidden nodes, as shown here. Right. So internal hidden node again means that it's adjacent only to hidden nodes. Right. So this graph is not exactly a tree, but I just want to illustrate the definitions of boundary nodes and internal nodes. So once we have this concept of internal and boundary nodes, then what you can show is that the connectivity and the impedances among the internal measure nodes can be easily determined from the Cron-reduced admittance matrix. So if you write things down, because the way you can organize your nodes now, then you can actually determine the connectivity and also the impedances of the internal measure nodes. Okay? The second thing you can show is that for every boundary hidden node, right? So you look at the boundary hidden nodes, and you look at the set of measure nodes connected to it, you can actually identify them. So you can identify, you can group the set of measure nodes by which unique hidden node they are connected to. And indeed, every measure node can be connected to at most one hidden node. And you can organize those measure nodes according to which hidden node they are connected to. Right? So we don't know where the hidden nodes are, but we know which groups of measure nodes that are connected to the same hidden node. So what this allows us to do is we can now write or organize the matrix, the admittance matrix, into this very simple structure, which then we can identify individual submatrices then of it. So it consists of the upper part are the measure nodes. So Y11, Y22, and Y12, Y21 are the measure nodes. The remaining 2 rows are the hidden nodes. So they are the boundary hidden nodes, the internal hidden nodes, but they are hidden nodes. Right? And the important thing are the 2 submatrices above, the Y11, Y22, and Y12, Y21. So these are the boundary measure nodes. In particular, Y12, Y21 are the boundary links. So these are the links that connects the boundary measure nodes and the boundary hidden nodes. And because of the second property we saw in the second slide, that we can now group the measure nodes according to which unique hidden node they connect to. Therefore, with this identification, we can arrange this Y12 into this form. It is broad diagonal, where each Y1 hat represents the admittances between the set of boundary measure nodes that are connected to the same, let's say the first boundary hidden nodes. So again, we don't know where the hidden nodes are, but we know this set of measure nodes are connected to the same hidden node. So we just call it, say this is the first one. And then the next group of hidden nodes, measure nodes, Y2 hat vector, is connected to the second boundary hidden nodes, and so on. And therefore, Y12, Y21 submatrix has this very simple broad diagonal structure. And therefore, because the row sum are 0, it means that the Y11, Y22 are also diagonal with the Y1 hat and Y2 hats and so on these diagonal entries. And therefore, the upper part, the measured nodes part of the original matrix Y has this very simple structure. And the important thing is that we can identify this this simple structure because of the properties the first property. And therefore, what the strategy is that we're going to try to identify Y11, Y2, Y1122, and Y1221. So those two submatrices on the upper panel. So that's the goal. And indeed, you can do that. And therefore, you can write down the equations and so on. And it turns out, as long as every hidden node is connected to at least 3, has degree at least 3, then you can indeed individually successively compute what those Y1 hat, Y2 hat, and so on. Once you compute all of each of these Yi hat, you can compute them from the Y2 bar, which we now know once we decompose the network, the Cron reduced network. And then we can treat all successive hidden nodes as boundary measure nodes. And therefore, we basically go back to the same structure, except now we expanded our measure nodes. And therefore, because some of the original boundary hidden nodes now becomes boundary measure nodes. And therefore, we can repeat until all hidden nodes have been converted to the measure nodes. So that's the idea. And that allowed us to compute the entire matrix Y. Okay, so that's the first talk. Let me now talk about a implementation project. So I will share my screen on my iPad. So let me stop.
Great, thank you.
Okay, so I'm trying to get my cursor so that I can stop sharing. How do I stop sharing? Okay, great. Now I share this screen. Okay, great.
Yep, we can see it. Thank you.
Okay. All right, so this is adaptive charging network for EV electric vehicles. It's work done mostly by my former PhD student, Zach Lee, who's now with the Caltech Star PowerFlex, Sunash Sharma, who's now at Berkeley, pursuing PhD, and Tongxin Li, who's a PhD student at Caltech. Okay, many people have contributed to this project over the years, and I just want to acknowledge them, especially people at PowerFlex that play a very important part. We work very closely with them to implement some of the things that I will talk about in their system. And also different summer students coming through Caltech. Okay, so I will describe both the physical infrastructure, the adaptive charging network, and also a research facility that would be on top of that, ACM Research Portal. So workplace charging, there are many reasons why we want to do that, and here's one. California has made a commitment to have, now is actually, has been revised up to have 60% renewables by 2030. When it first proposed, it was 50%, but now it's more ambitious to have 60%, and 100% clean electricity by 2045. And to have 5 million electric vehicles or zero emission vehicles by 2030. And for those of you who know duck curve, and this is the duck curve in 2021. So it's, and if we want to fill the valley of the duck, then you can charge 13 million EVs. So there's a lot of opportunities to combine two problems, the duck curve problem and also the EV, which is going to add stress to the network into a solution. And also there's some surveys that shows that drivers are twice as likely to get EV when workplace charging is available. So they won't buy an EV because the workplace charging is available, but you can tip the balance. Okay, so here's a physical system. The Caltech has for such a small school, has a pretty large electricity infrastructure, and we actually generate 100%. That's zero energy, not emission, but that's zero energy last year. So there's a main switch panel at the garage. From that, we built two 150 kVA transformers, and then the breakers and panels and switches and so on, and eventually bring it to the smart chargers here. And so the smart charger is built by George Lee, a former student at Caltech, using open source, originally open source chipsets. So that's the physical system. The cyber system is as follows. When the driver plugs in his car or her car, she can use a mobile app and let the system know two pieces of information. How much energy does she need? So I need 30 miles. And when do I expect to depart, say 5 p.m. today? And therefore, the system knows the energy demand and also the expected departure time of every EV in the system. So this information is sent to the cloud, and every minute, the cloud will form a quadratically constrained quadratic program, which is a convex problem, and solve the optimization, and then that would determine the charging rate, RIT, for every EVI at time t. So this is model predictive control, and therefore every minute you form a optimization that look 12 hours into the future, every minute in the next 12 hours. And then solve the optimization problem and use the rate for the next minute to actually charge your EV. And then the next minute comes around, you repeat the process. So that's the cyber system on top of the physical system. The first deployment is 2016. It was 54 programmable chargers. So that's George. And that's the original charger. Now it's replaced by commercial chargers now. So by July 2020, it has delivered 1 gigawatt hour of electricity, equivalent to 3 million miles or 1,000 tons of avoided CO2. Then we deploy it at other places, JPL, and the startup was acquired by the EDF, which is one of the largest utility companies in the world, based in France. So just show you some pictures. This is the picture of the charging rate as a function of time. So this is time, this is M, the charging rate. Each color represents AEV. So you can see that its EV charging rate fluctuates. So this was January 2018. This is a deployment at NREL. So many businesses, they pay not only for energy, how much kilowatt hour they consume, but also the power. So this is a demand charge based on the peak power during the previous billing period. So what we want is to control the EV charging, to control the peak power. So this is the net load. So the building load minus the PV, on-site PV. Over the weekend, there's not a lot of building load, and therefore you see this dark curve. During weekdays, you still see the dark curve, but it's much higher level and much more fluctuation. So despite the fluctuation, you are able to control the net load, which is the building minus the on-site PV, plus the EV, which is this portion, so that the peak power stays below 40 kilowatt. This is the impact of COVID, March 16 of 2020. So that's the physical infrastructure. And then on top of the physical infrastructure, we want to build a research portal, which is a research facility. And the motivation is that when we first started to build the system 2016, it really is a test bed. People charge for free, and we try different things on the network, things break, and everyone is fine because it's just a test bed. By 2018, it has transitioned to commercial operation. And therefore, we no longer can do anything we want on the test bed. And therefore, the idea is to build a software layer on top of the physical infrastructure to provide three things for research. One is ACM data, and then the ACM Sim and ACM Live. ACM Live is not completed yet. ACM data is basically we automatically collect the real-time charging information. So it's not just a session data that is how much energy and the departure time, but also the exact charging rate for every EV in the garage every 10 seconds or so. So it's a fine-grained, large-scale EV charging data. We automatically collect them, clean them, anonymize them, and then put them on the web. So everything is open source. We also developed a realistic simulator for this infrastructure so that if someone come up with a new charging algorithm or even a pricing algorithm, they can simulate this without having to implement all the basic infrastructure for the simulator. And then ACN Live, I'll tell you a little bit more later on. Okay, so ACN data. So this is October 2020. There were 53,000 EV charging sessions. And again, each session contains not just the session information, but also the time series of charging rates in amps every 10 seconds or so. It's growing daily and publicly available. You can use the data for example, monitoring user behavior, evaluating different charging algorithms. You can evaluate the charging facilities. You can evaluate if you have a lot of smart charging garages on the feeder, what is the impact to the grid? So let me just show you some of these applications of some of this data. So this is the user feasibility that Lexity is basically how much spare you have in terms of how long you stay and how much energy you need. Right? So Caltech weekday, you can see the Lexity is more than an hour. Weekend is slightly lower, and JPL weekdays and so on. So you can see in terms of the user behavior, you can extract that from the data. You can use it to evaluate the flexibility of the infrastructure. So at Caltech, for example, compared with uncontrolled charging, optimal scheduling can save you more than 3 times, close to 4 times of, say, the infrastructure. So this is the P rate that you need to support, which translates into how much distribution system capacity you need. And therefore, it translates to both the capital cost, but also the operating cost in terms of demand, if you have to pay demand charge. And JPL also is more than 3 times savings. You can also look at user behavior. When we start payment, then the charging number of sessions drops. When there's a COVID, then there's another big drop. Post-COVID, for example, you can see that the distribution of the arrival times has a larger variant. It probably means that it's because people have more flexible hours. You can also look at the detailed time series of the charging rates. Now, for example, in this project, the thinking is that even though we have 35,000 charging curves, they only really come from a small number of batteries used by a small number of drivers. And therefore, we should be able to characterize or classify this large number of charging curves into a few groups. Can you do that? Well, it turns out it's a very challenging learning problem because we do not know state of charge of the network. All we see will be the charging currents going to the car. And therefore, it's a little bit tricky how one can do that. But it makes a very nice, interesting learning problem. So I will skip the details. So that's the ACN data. You can use it for many different purposes, and people have been using that for various research problems. The second thing is ACN Sim. So we build a realistic simulator that simulates the charger, the EVs, and also the battery. And you can use different battery models. And there are many battery models with different fidelity and complexity. And you can swap the in and out different models. And also different constraints connected to, for example, the charging facility. You can also take the ACN data, the real data that drives the simulation. You can also take external signals such as utility tariffs. Maybe you want to charge in a way that will minimize your electricity bill for the site, for example. You can use solar generations either on site or let's say in CalISO. The idea is that maybe I want to charge at a higher rate when there's a lot of solar generation in real time, for example. And the ACN SIM will provide a very simple interface so that if you have your own charging algorithms, then you can just interface with the ACN SIM and you don't have to implement all these basic facilities and can easily evaluate how your algorithm compares. When you are happy with your algorithm, it's all safe and so on, we can actually allow you to run your algorithm on real cars at garage, at Caltech Garage. So this is ACN live testbed. It has the same interface, but underlying that is a real garage plus some checking layer instead of the simulator. And therefore, your algorithm doesn't even need to change. Once you're happy with this simulation, then you can just run it on ACN Live. So that's the idea. So the idea is that this layer, when you issue a charging command, this layer will check whether your charging command is safe. If it is not, then you would use its default. Yes.
Right. Yeah, there's a question from IBM. So Jeff Katz from IBM want to know, has this work shown some secondary benefits such as FAISR? Jeff, you can unmute to ask directly if you want. But yeah, Stephen, do you have any comments?
What was the?
Yeah, the question I can repeat.
Okay.
Oh, what is
FAISR?
Yeah, Jeff, do you want to unmute to elaborate?
Yeah, what is FAISR?
Oh, sorry, it's fault location, isolation, and service restoration.
Oh, I see.
It's a term utility companies use. I was just wondering with some of the simulation and you know, and other better uses of the available data, was there a secondary benefit to this work in you know, that area of utility operation?
Right. So we ourselves have not looked at that particular benefit. What we have done, though, is to use the data to simulate the impact on the grid. So, for example, we have a certain grid, yes, and then you have certain number of such smart garages and with their capacities and so on, and then you can
Right.
simulate what is the impact. Yeah, but I assume you
No,
can.
I understand what you were showing. Yes.
Yeah. So, but not that particular benefit.
Okay.
Okay.
I just thought some of the work might help in the operational aspect. Okay.
All right.
Yeah.
Yeah.
Good idea.
Okay.
Okay.
Yeah.
So.
Oh, sorry. There's another question, Professor Low. If you don't mind, I will raise them here.
Yeah.
Are you okay? Yeah. So yeah, there's a question from PNNL from Dr. Qiu Huang. He was asking, how do you ensure safety and reliability of the charging actions? For example, you do some actions, how what can be wrong, and how are you going to avoid?
Right. So first of all, let me, as I mentioned earlier, the design is complete, but the implementation of ACN Live is not. And that's because we need to work very closely with PowerFlex, and there's some delay on the PowerFlex side. For good, I guess for good reasons. The PowerFlex, they expanded a lot of their operations, and therefore this becomes a low priority thing for them, and therefore we haven't actually implemented it. But the idea, the design is as follows. So, and therefore there are assumptions. What we assume is that we do remember what the actual system does is that every minute it forms a QCQP. And the QCQP is supposed to capture the operation of the charging facilities and all the EVs and so on. So we assume that QCQP with all the information in that QCQP accurately capture what is needed and what are the constraints in the garage, which in practice it does, because that's how this actual system charges. And therefore, the way we check safety and so on is to say we have a QCQP that normally the PowerFlex system will actually use to determine the charging rate. If I replace the charging rate by your charging rate from your algorithm at this time, And then going forward, will the problem still feasible, meaning that would all the EV demand charges, energy demands still be met before the deadline? If it can, then we'll pass your charging commands to the cars, and then we measure the state changes, we send it back to you, and your algorithm can continue. If we take your charging rate, plug into the QCQP, and then it turns out that we will not be able to satisfy the energy demands within their deadlines, then we will ignore your demand. We will charge using the same charging rate that PowerFlex system would have. So that's the idea.
All right. Yeah. Qiuhua, do you have any question? Please feel free to unmute. Otherwise, I will let Stephen to continue.
Thank you. Thank you.
All right. Thank you, Qiuhua. Yeah. All right, please go ahead, Professor Lo. Thank you.
Okay, sure. Yeah, please feel free to just unmute and ask questions. So there was a question, there's level 1, level 2. So most of them are level 2. There's some DC fast charger in the garage, but not level 1s. All right,
okay,
great. Let me continue. So that's the ACM Life. And again, everything's open source, it's extensible. So we're looking for people, hopefully some of this can be useful for your research, but if you want to actually take a lead on contributing code or even taking the lead on maintaining, that would be great. Okay, so you can find more information at this website, and Zach Lee, who is now at PowerFlex, but he still helps maintains the site. So please feel free to reach out to him or to myself. Okay, so let me see, what time is it?
Right, it's 1 hour. If you want, you can talk for 10 or 15 minutes. Yeah, no worry.
Great. I will go through this quickly. So it's really a work of Guan Nanqiu, who was a former student at Caltech, is now faculty at CMU. So it's voltage control and distribution network. So the problem is that you have a voltage that you need to maintain at every point of the network to within a certain nominal values. And because of the generation, say distributed generation, the loads and profiles and so on, you could have some voltage violations. And what you want to do is to control it so that the voltage violations can be removed. So that's the basic problem. There's a lot of progress in the past decade on this problem, and there are many different proposals, even standardizations. And many of those proposals, including our own work, assume full knowledge of the network topology and also the impedances. They often also use linearized model. So this flow model is a very nice model proposed at Berkeley back in 1989, but by Baran and Wu. So we use it ourselves, and we use linearized model for some of our work here as well. Now in practice, of course, topology may change. The line parameters may be unavailable, right? So that was the first part of the talk, that we may not know them. The linearized model is an approximation. In reality, we do have nonlinearity. Okay? And therefore, how do we deal with this lack of model information and also nonlinearity? And Guan Nan's approach is to use online learning to deal with unknown models, and also Jacobian tracking. That is, you will have a way to track or estimate Jacobian continuously based on the feedback information to deal with nonlinearity. So let me explain. So this is the problem formulation. We have a distribution grid is a tree topology single phase, and therefore the disk flow model applies. The voltage depends on, among other things, so assume the real power is given, so that's a deterministic quantity, but QT, which are the reactive power at nodes where you can control the reactive power, say smart inverters, for example, Q of T. So the Q of T is the control, which you can determine using some control laws, which you would design. Based on the control, the network will basically solve a powerful equations and produce a voltage which you measure. So that's the feedback control, that you measure the voltages on the network. Based on the voltages in the network, you determine the next control action Q of t that got fed to the network, and the cycle repeats. So that's basically the basic model. What is the goal? The goal is to choose the Q of t, the control, so that in steady state, not during transit, but in steady state, you will minimize a certain cost that can be expressed in terms of a quadratic form in the vector Q in steady state. And that the voltage in steady state will stay within the safety limit, right? So within this, say 5% of the nominal value. And therefore you can represent this by some function V of Q lies between a certain range, 5% of the nominal value. So that's the optimization problem. And therefore what we would like to do to design this feedback control is so that in steady state, Qt will converge to an optimal solution of this problem. Now, the challenge is that the V of Q function is nonlinear, is non-convex, therefore the problem is a non-convex problem. Now, let's take a closer look at the V of Q function. In previous studies, many previous studies, including our own, we assume V is a linear function of the control Q. So P is a given, P represents the real power injection, which we assume is given. So this is real-time control. And there's some parameter V base, which also is given. So typically that's the assumption. So we know everything in this equation. We know the matrix X, matrix R. So these are the two matrices that depend on the topology and also the impedances of on the lines. Now, in reality, is not just the linear portion, but also there's a nonlinear portion, and there's no explicit form. We don't know that, for example, right? If you assume it's the original this flow, then we do know the equation. But in general, it can be any nonlinear function, which we may not know. And therefore, this is a pretty general model because we can just take the actual voltage measurement minus the linearized model, and the remaining we just call them nonlinearity, right? So it's pretty general nonlinear model. So, but we don't allow arbitrary nonlinearity. Is a structure. Structure means that V of Q can be any function of Q, but that it needs to be differentiable. That's the assumption. And it also Lipschitz in Q, right, with the Lipschitz constant L. Moreover, the Jacobian dVdq is Lipschitz with a Lipschitz constant L prime, right? So that's the assumption. As long as V of Q satisfies these two assumptions, then V of Q can be any function. So this generalizes the linear function and captures a certain degree of nonlinearity, right? The nonlinearity is limited by the Lipschitz condition on V of Q and is Jacobian. So how do we do voltage control with this nonlinearity and without the model? So let's look at the simple case where we do know the model. So this is a case that Guanan also looked at in 2016. And here's an algorithm that is optimal. So there's this essentially Lagrange multiplier. So this is basically the dual ascent algorithm for that optimization problem that we showed earlier. So there's a Lagrange multiplier associated with the upper bound, with the lower bound, and then you compute, which you update according to this simple update rule, and then you compute your control Q of t in this manner that depends on lambda of t, and this x is the Jacobian of V with respect to Q. Now, if we assume we know the model, and in particular, the model is simply the linear disk flow, then we can write down the matrix X explicitly. And therefore, I can implement this dual ascent algorithm. And Guanan shows that indeed, you can show that this feedback system will converge and solve that optimization problem in steady state. Now, how do we generalize to the case when the network is unknown and the model is nonlinear. So the idea is to compute an estimate of the Jacobian. So we don't know the network, and therefore we don't know the Jacobian X, but we will try to compute a matrix X hat of T at each time T that is meant to track the Jacobian. So that's the idea. Right? So we want this X hat of T to track J of T. Then what Guanan shows, meta theorem, is that if the error is small enough, in particular, it is smaller than this expression, then indeed any limit point of this system, so lambda T is simply the vector of this, okay? Then the primal and dual algorithm will converge and solve both the primal and the dual problem of the optimization problem we saw earlier, right? And therefore, the key is that you have your Jacobian tracking matrix has to be accurate enough, okay? So how do we make sure that that's the case? So here's an algorithm that Guanan proposed. There's the excitation noise, and then you compute and update your X hat of T plus 1 in terms of X hat of T and the other measurement quantities. Now, how do we understand this? Well, you can show that the X hat of T can be thought of as a minimizer of past errors, exponentially weighted. So you have exponential discounting, but you look at all the past errors and you will choose the X hat that will best match, will minimize the error. So what is the error at each time before time T? So this error term can be thought of as accounting for the error of two types of error. One is the nonlinearity, one is the excitation noise. Both will produce a certain error, and you look at the exponential discount version of all these past error, and you choose a matrix X hat of T at time T to minimize that. And that's how you would do the tracking. Then Guanan shows that indeed, if you do this tracking, the error indeed satisfies what you need in the meta theorem. And therefore, combining with the meta theorem, then if the step size for the dual variable update is small enough, then every limit point of the primal and the dual variable will converge to an optimal pair. So let me close with some simulations. So this is a simulation of a Southern California Edison distribution grid. If we assume the network is linear and we can compute the actual dual ascent algorithm exactly, but if the network turns out not to be linear, so we assume the network is linear, we compute the Q, the control, feed it into the network, but the network is non-linear, then you can see that the cost will not be optimal. Whereas if you do Guanan's approach using this learning augmented control, voltage control, then indeed you can minimize the cost. This is the voltage profile. It works. So to summarize, what Guanan shows is that by combining learning with the feedback voltage control, you can indeed handle the case where the network is unknown and also includes some linearity. And the main idea is to use this structured black box view for bounded nonlinearity, and then carefully design a Jacobian tracking matrix. Okay, I will stop here. Thank you very much. So
right. Thank you, Professor Lo. Yeah, I appreciate your time. Yeah, very comprehensive with 3 parts of the talk. So now I will pass the question to you from Ken Crawford Ford. So he was asking, is the method for Y matrix estimation at part 1 applicable to unbalanced 3-phase distribution system?
Right, so if it is balanced, then we can just look at single phase, the per phase model of the system, then it will be applicable. If it is not balanced but it's symmetric, meaning let's say the lines has some symmetry, and the impedances are the same and so on, then indeed you can do this symmetrical component and just look at the positive sequence network. Then that you can treat it as a single phase network. Then the first part will also apply. Now, in practice, of course, it is three-phase unbalanced. But if you just look at this positive sequence network, just ignore the other negative sequence and zero sequence, then it is an approximation. You can still apply the first part to the positive sequence network. Whether the approximation is good enough just depends on how bad or the imbalance is.
All right, very good. Yeah, Ken, are you okay with this answer? Feel free to unmute. Otherwise, I will go to the next one. All right, Ken said, thanks, that helps. Qiushi, do you have any question on your side?
Yeah, hi, Yang. Yes, I do have two questions here at my
Okay.
side. The first one, what if the hidden nodes have a degree less than 3?
Right, so what happened is that, imagine if you have a hidden node that's connected to two hidden nodes, then we will not be able to identify this node. And therefore, it will be equivalent to, there's no hidden node, it's just two nodes connected directly in that through that intermediate hidden node with degree 2. So that's what it is. That is, if a hidden node has only degree 2, then it is possible you will not be seen, basically. So that will be the error that is incurred.
Yes, I see. Thank you.
But it turns out that as long as it has degree 3, you can always recover exact Y matrix.
Yes, I see. For the second question, can you please talk more on the code support for ACN theme? So what kind of algorithms or what are you looking for? Yeah.
What kind of algorithm? Okay, sure. So yes. let me see.
Yeah, people are interested in that.
Yeah, sure. Let me discard. The algorithm is, sure, I can talk a bit more. Is okay. So this is the algorithm. A couple comments. It's pretty simple. It's simple conceptually in the sense that it is a convex problem. It's QCQP, quadratically constrained quadratic program. And therefore it is a convex problem. And typically in a garage, I think that maybe the largest deployment that I know, I'm no longer very much in touch with the company, so I don't know the latest development. But when I was still involved, I think the largest deployment we had is something like 100-something EVs, perhaps. And therefore, it's not a large problem. So it's convex, the size is not that great, and therefore you can solve it. The size, the limitation to the size is really that you have to do this MPC for 12 hours into the future. So that's a lot of time, and therefore the size is not trivial. Okay. The second comment is that what are the cost functions of the constraints? So the cost function depends on the site. So for example, some sites wants to minimize the electricity cost to them, which may depend on the electricity tariff, may depend on the on-site solar generations they have. Some sites want to minimize, in addition, also minimize the demand charge. Some sites want to just charge as fast as possible, right? So you have different, you could have different objectives that the sites want to implement, which you can incorporate in the cost function. In the cost function, we also have some regularization terms that will, for example, try to smooth the charging rate. You don't want the charging rate for every EV to just fluctuate drastically and unnecessary, for example. So there's some regularization terms you can put into the cost function for those kind of purposes. So what are in the constraints? So the first thing in the constraint is that we want to satisfy energy demands for every EV before their deadline. Now, what happens if it is not feasible? Like the problem is not feasible, then you can relax that by having inequality, for example. But then you have to do it carefully so that you don't. The optimal solution is not zero every charging rate, for example. But you can deal with those kind of things. The second type of constraint is the capacity constraint, which is actually this looks like a linear. So this capacity constraint can represent things such as this breaker, for example, has a certain capacity, or this transformer has a certain capacity. This switchboard has a certain capacity, so you can do it. So originally, all the capacity constraints were linear, were assumed to be linear, but later on we changed it to it turned out to be second order cone, and this has to do with the three-phase nature of is a three-phase delta configuration on the charger side. And because of that, you can show that that gives you a second order cone capacity constraint. And then there's some other constraints for some other things. For example, you can implement priorities and so on. But basically, you can adapt the objective functions and different set of constraints for different purposes that depends on the site.
All right.
Okay.
Good.
Thank you.
Thank you. Yeah, that's all for my end.
All right. Yeah, the next question comes from Professor Ali Abu from Northeastern University. Yeah, he was asking, what is the time interval between T measurements in estimating the Y? So that's the first one. The second question is the VT matrix always well conditioned?
Right. So unfortunately, let me see if I can. So the let me try to stop this. Okay. Let me try to share screen on this one.
Okay.
Oops. Can't find my screen. Okay, never mind. All right, so so the quick answer is unfortunately I don't really know, because we there were some simulations, but we don't have real data now, and therefore I don't know in practice how many measurements you need to get so that your measurement matrix V is sort of rich enough. So mathematically, what we need is the column. Once you lay out the V matrix as I shown, it's full column rank. So that's what we need. Now in practice, how many measurements do you need to get that? We don't really know in practice. I assume if you assume a certain certain statistical models on the measurements, some noise models and so on, one might be able to estimate sort of the sample complexity, but we haven't really looked into that, so I don't know the answer.
Okay, all right, thank you. Yeah, Professor Ali Abu, if you have any additional comments, feel free to unmute. If not, I can also ask the next question. All right.
And therefore, I also don't know, I guess, that whether the VT is well conditioned or not. we just don't have real data. Sorry, go ahead.
Okay, yeah. All right, so maybe, yeah, Professor Ali Abu, yeah, do not have any further question. So yeah, next question is coming. Oh, yeah, Professor Abu, are you going to say something?
I'm fine, thank you.
Okay,
Thank you.
appreciate it. Okay.
Thanks, Ali.
Yeah, okay. Yeah, the next question comes from me. So in your first part, you were talking about how to identify the topology connection, even with some hidden nodes, to be unobservable or no measurements. And in the later part, maybe part 3, you were talking about, oh, maybe you cannot have the topology, then you still want to do some maybe learning-based control. So I do have the question. Yeah, so in general, yeah, in some part of the network, you probably can use your strategy in part 1 to identify all the topology, but maybe not in the other area. So what is the overall framework? Are you always going to identify where they are the hidden nodes, that you can identify the topology, then you dispatch the traditional control to regulate? And for the other part, yeah, maybe there are 1,000 buses, but only with 100 measurements, there it's impossible to recover. Then you say, I cut the network. Yeah, I do some learning-based control in the other part. So do you have a framework or some conclusive comments here?
I see. Great question. Quick answer is we don't. We have not looked at that, but I think it's a really